Okay, today I'd like to continue our discussion of high gain, single stage op amps. Here's where we're at. We've talked about single stage low gain op amps for the first about 4 lectures or 5 lectures. We started on single stage high gain op amps last time. We'll continue on that today. We'll continue on that on Wednesday as well. A review from last time. This is kind of important enough I wanted to bring it back up again. We talked about different ways to find the 2-port model for the 2-port network. And we said one way to find the 2-port model is just to calculate the voltage gain. And we can read off the key parameters, the GM and the Gout, then from this single pole expression that we'll get. If we put one capacitor on the output, it'll be a single pole system, and we can read off G and GM. Recall also that if we have a half circuit, once we know the 2 conductances, G1 and G2, and the conductance GM, the voltage gain was minus GM1 over 2G1 plus G2. The bandwidth was G1 plus G2 over CL, and the gain to bandwidth product was GM1 over 2CL. We talked about this on the second lecture. I just want to keep reinforcing the fact that if we get these parameters of the 2-port, we can get the parameters of the half circuit. And of course, we get the parameters for the whole op-amp circuit as well. Recall also when we decided to look at trying to increase the gain of the op-amp, we went back to the quarter circuit and asked the question, what can we do in the quarter circuit to increase the gain of the quarter circuit? Because the op-amp parameters were almost identical to those of the quarter circuit. And last time we went and looked at the Cascode circuit. The Cascode circuit, so the argument was, if you want to increase the gain of the half circuit, which is derived from the quarter circuit, we can either increase GM1, or we can decrease G1 plus G2, or both. So what we did last time was with the Cascode circuit. What did we do with the Cascode circuit? Jake, what did the Cascode circuit do?
It decreased G1 and G2.
It decreased G1 and G2 and stayed the same. GM1 stayed the same and G1 and G2 decreased, so that resulted in a net increase in gain. No improvement in gain bandwidth product, if more is better, but no deterioration either. And that resulted in this structure right here. And of course we said that and here was the gain expressions. And how long did it take us to get those gain expressions? We wrote them down by inspection, didn't we? Once we had that Cascode circuit analyzed, we wrote down the gain expression for the telescopic cascode amplifier by inspection. We didn't call it a telescopic cascode amplifier. This is just really the Cascode circuit converted into an operational amplifier, and then we named it the Cascode configuration, or the telescopic cascode configuration. We also pointed out that we could have either P-channel or N-channel inputs. And we first looked at this one way, and we says, well, instead of driving the quarter circuit, we can drive the counterpart circuit, and then set the quarter circuit up as a current source. And if we do that, we then have the P-channel inputs. Or we could have started out with our Cascode circuit made of P-channel devices, and we could have called that the quarter circuit, and then this would have naturally been the counterpart circuit for that, right? We could view it either way, either driving the counterpart circuit or starting with a different quarter circuit. We've got a question here. How important is it to develop a good approximate analysis method for an op-amp with the complexity of the telescopic cascode structure? We wrote down its gain characteristics by inspection. I think Miss Elva, in fact, gave us the gain expressions for this device. And of course, we're going to have some circuits that are somewhat more complicated than this telescopic cascode amplifier. So the question comes up on how important it is to have simple expressions for those and simple analysis procedures as well. So I'd like to go back to this circuit a little bit again. And this is a little bit more complicated than what you did in homework assignment 1, where you analyze the 5-transistor circuit. And when we analyzed this circuit, we were able to get these simple expressions by making primarily 3 assumptions. We assumed that the AC voltage was 0 on the approximate axis of symmetry on this circuit. I call it approximate in this slide because I've got a little bit of asymmetry on that current mirror on top. If I take the current mirror biasing off, then I would have a symmetric circuit, but I have slightly asymmetric. I've assumed that the left and right sides are matched, and I've assumed that the current mirror really mirrors the signal current from the left side to the right side. We talked about that a little bit more last time. So I've kind of made 3 assumptions that allowed me to get these expressions by inspection. We can ask the question, how much more involved would an exact analysis be? And would an exact analysis provide additional insight? So this weekend I had some fun. I decided I'll do an exact analysis for the circuit. You did the exact analysis for the 5-transistor circuit. I'm going to do the exact analysis for a 7-transistor circuit. Just add a couple more let's see, 1, 2, 3, 4, 5, 6, 9-transistor circuit. I've added a couple more transistors in. And it's pretty easy to put in the small signal model. I just copy and paste the small signal circuit and interconnect them together, and I've got the small signal model. That's straightforward. 15 minutes, you probably write down that small signal, draw that small signal equivalent circuit, or less. It's tedious, but it's straightforward. You can be watching a football game and draw this circuit and probably not make any mistakes. And if you look at this circuit, I have non-critical nodes at the top, here, 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 and here. So I have 7 critical nodes, 7 nodes in the circuit that are not input or that are not an input. So I can sum currents to those 7 nodes using Kirchhoff's current laws, and I get these 7 equations. And I made a mistake or 2 on these because I was probably thinking about something else when I write in the equations, but I finally cleaned them up. So this is a bit tedious, but really straightforward, right? There's not too many branches there. The time required to obtain the set of equations is pretty small. In matrix form, and I should have given some more thought to how I write which order I put the equations in this list. But in matrix form, A indicates the presence of something that's non-zero. So really this set of equations is of the form some matrix A times the 7 unknown voltages in that circuit, the 7 nodal voltages, is equal to something times the excitation vector. And there's 49 entries in this matrix. 2/3 of them are 0. And in fact, most of them are close to the main diagonal. I didn't write it in a way to see that, but you can rewrite it in a way that most of them are close to the main diagonal. So the fact that there's so many that are 0, and the fact that you can reorder these in a way that most of them are near the main diagonal, means that there's a dramatic reduction in complexity of exact solution of these equations. If this is a diagonal matrix, then we just solve one equation at a time and we're done, right? If it's nearly diagonal, it dramatically simplifies the analysis. So this is not too far from diagonal, a little bit. But there's still quite a few off-diagonal terms. There's like close to 20 terms, and 7 are on the diagonal, so we've got quite a few off that main diagonal. So this is dramatic reduction in complexity compared to what we'd have if a bunch of these zero terms were not zero. But I don't think anybody was able to solve that 5-transistor circuit in the 30 minutes for homework assignment 1. Did anybody get it in 30 minutes? Closed form solution. Okay. So I wrote MATLAB code. Here's a MATLAB code for obtaining all the outputs as a function of the two inputs, Vn plus and Vn minus. And I'm not an expert on MATLAB, but it doesn't take long to write this MATLAB code either. Simple MATLAB code. Okay. And it's a simple program, and the effort required to write it is small. If I'd be writing MATLAB code on a regular basis, I probably could have written this in 20 minutes or 15 minutes. Since I haven't done it very often lately, it took me a little bit longer to write this code. And I did the same thing for the differential input. Instead of having Vn plus and Vn minus, I put in V differential input. So I just have one input. Now, if I want to get the total analysis, I can either do Vn1 and Vn2, and that'll get me the two gains A1 and A2, or I can do Vn common and Vn difference. So I'm just doing Vn difference here. I did not put Vn common. Equations are about the same. Simple program, small effort. Then I clicked run. And I got the output. And this is the output for Vn plus and Vn minus. And this is a MATLAB. Oh, I didn't quite get it all on one page. Whoops, I didn't quite get it on one page. Whoops, I didn't quite get it on one page. Now, these are not new runs. This is the same run. And I had to find a way to, I couldn't get the output in the command line, in the command line on MATLAB. It said that there was too many characters to display. So I had to use the diary function. You notice there was a diary command in there? Everybody's familiar with diary command, right? That's not a good news when you have to use diary command. Oh, let's continue again. And again. Oh, I'm partway done. This happens to, everything in black happens to be the numerator.
Use the simplify command.
And here's this is continued 7, continued 8, continued 9. Oh, I finally made it. On 10 slides, continued at 9, on 10 slides, I finally got the solution. I've got the exact solution. It's more exact than this simple expression that Miss Elva helped get in 3 minutes last time. Okay? It's more exact. So we finally got the complete analytic expression. Let's go zoom in a little bit on it. So I'm going to zoom in with the transition. Here's the divider sign between the numerator and denominator part. And I'm going to zoom in and put the end here, just to look at what's there. So I zoom in at that transition point. Here's V and P appearing. And there are 1, 2, 3, 4, 5, 6, 7 conductances multiplying V and P in that term. And of course, here's another V and P. There's 1, 2, 3, 4, 5, 6, 7 conductances multiplying that term. In fact, if you go up the list, there's 7 conductances multiplying every V and P or every V and N. And the denominator polynomial, 1, 2, 3, 4, 5, 6, 7. 7 conductances in each term of the denominator polynomial as well. And down here, towards the end, notice that I have an SCL. I didn't factor out the S, but there's an S and S and S and S and S and so forth. So this is that coefficient of the S term in the denominator is first order. And then if I go up farther towards here, there's no S appearing. That was the constant terms. And then the last couple of pages were the S terms. Okay? Exact solution. There are approximately 2,000 factors in the output characteristics. 2,000 of these terms here that have 7 conductances in them. There are approximately 14,000 small signal parameter appearances in this expression. And this is for the output voltage. The gain bandwidth product's much longer because now we got to go back, go take this gain expressions and multiply it by the bandwidth. The bandwidth is another 5 or 6 pages long. So we could write that expression out in 15 or 16 pages. And we'd probably have 20,000 small signal parameters expressed here. Have we made progress? No, I don't think we've made progress. It's the exact solution, but it's going to be difficult to get insight into what's going on. And if you just make a mistake in one of those subscripts in these 20,000 terms, you got a problem. Do you have any insight into how the circuit operates by looking at this more exact solution? Probably not. So I did the differential analysis. Differential analysis was a little bit easier. Here's the solution for the differential analysis. Those few lines of MATLAB code as well. Continued once. Oh, it didn't. I only had to have this on 6 pages instead of 10 as before. Of course, I only have the difference mode gain. I didn't get the common mode gain yet. So if I go back and do that again, I probably have another 5 pages of equations. So this only has 1,100 product terms, 7,700 transconductance expressions. So, how important is it to develop good approximate analysis methods for an op-amp of this complexity? So what do we really end up with? Of those 2,000 terms, we kept about 3 in our approximate analysis. And that approximate analysis is very good. If we wanted to, we'd go through those 7,000 terms, and we could find out which 3 we should have kept. How long is it going to take you to go through that group and convince yourself that all these other terms are negligible? A long time. And what's even worse is that many useful op-amp circuits will have even more complexity. This telescopic cascode op-amp is a pretty simple op-amp. What do you think happens if we add 2 or 3 or 4 more transistors?
See an exponential increase in terms.
Yeah, diary might have exceeded the... Okay? So let's go back and ask the question, are there other high output impedance circuits that can be used as a quarter circuit? So we started out with the single transistor as a quarter circuit, made a pretty good op-amp. It's our reference op-amp. Then we went to the cascode configuration, a 2 transistor structure, and it resulted in a big increase in the gain. So let's go back to this expression here. Reason I asked a question before we started, there's something called the regulated cascode structure that's oftentimes discussed in an electronics course. We choose not to discuss it in 330, probably not in 230 either. But the regulated cascode is another basic simple amplifier structure. And here's what the regulated cascode looks like. So you start with a cascode configuration, but instead of connecting the gate of this transistor to an AC ground, we put an amplifier in between the source and the gate. And we call this structure the regulated cascode. Or some people call it the gain boosted cascode. Okay. The amplifier A is usually a simple amplifier. Often the reference op-amp. Often we'll use the reference op-amp, the 5 transistor op-amp, for the A amplifier here. And I'm assuming it's bought the DC current source. I'm not showing it here, coming into this quarter circuit. Okay, so this is the regulated cascode structure. I can then analyze this regulated cascode. So here's a small signal equivalent of the regulated cascode structure. We're going to use this as a quarter circuit in a minute if it's got interesting properties. So I put in the small signal models just like I did for that telescopic cascode, but in this case I don't have to use MATLAB. I can sum currents at this node and at this node, and I get these two equations, and I can observe that the voltage at the input plus Vx is equal to the gain of the amplifier times Vx. So I get three equations. These are not hard equations to write. And I can easily solve these equations for V out. Okay. And if I solve those equations for V out over V in, I get this exact expression. And then if I observe that G outs are small compared to the GM, and that A is large, and I assume A is large, I get V out over V in is equal to minus GM1 over SCL plus G out 1, G out 3 over GM3 times, well, I guess A. If I this is exact, this approximate here, and if A is large, I can replace 1 plus A by A. So I get this expression here. And I can immediately read off from this expression then what the GM is for the quarter circuit, because the GM always sits in this position. And I can read off what G is for this quarter circuit, because it always sits in this position. So now I have a two-port model for the regulated cascode. Let's see what I've done. How does the GM of this structure compared to that of a single transistor circuit, this PUN? How does the GM of this compare to the single transistor circuit? George? They're the same. Single transistor circuit had a GM equal to the GM of the transistor. George, how does the output conductance of this circuit compare to the single transistor circuit?
Smaller.
It's smaller. In fact, how much smaller is it?
The factor of 1 over A G out 3 over GM3.
Yes. In fact, this was the output conductance of what?
The cascode.
The cascode. So we're taking the output of the cascode, output conductance of the cascode, and we're dividing the output conductance of the cascode by A. So this output conductance is smaller now than that of the cascode by another factor of A. Okay, so in fact, if A and GM over G out were about the same, which would happen if we use a simple op amp for this, then we decrease the conductance by about a factor of A squared. Make sense? So does this look like, at least from a small signal domain viewpoint, does this look like it offers potential for increasing the gain of our op amp even more?
Yeah.
Okay? Now keep in mind, we're doing synthesis again. We're doing synthesis again, and we're going to write down characteristics of our op amp by inspection. Yes?
What's a large A, like numerically? What would be a large A?
Whatever you want. But oftentimes you'll use the reference amplifier to build A. Or you'll use an inverter to build A. And that would have a gain of about GM over G out. GM of a single transistor over G out of a single transistor. Okay. So G out equivalent, we've got there. So based upon the small signal analysis, it appears that the output conductance has been decreased even more than what we had for the cascode configuration. Here's the gain expression. We had that to start with. We can read off the gain and read off the GAN bit. And it has the same gain width product as before. The bandwidth decreased, the gain increased in such a way that GB stayed the same. Of course, we got to be careful because looking at things in the small signal parameter domain can sometimes fool you. if we compare things in small parameter domain, it may be the case that the powers are different or something else. So I'm not going to go back and look at what happens if we put in the practical parameters that we're ready to do. If I do it like I did for the Cascode configuration, verification will show the predicted improvements are achieved with the structure as well. Almost. We're going to get a big increase in the gain, but there's one little bit of caveat there. Those A amplifiers don't come for free. One of our most valuable resources is power. And previously, once we set the gain, we used the power to set the GB. GB increased literally with power. All of the power went to establishing GB. Here, we have to funnel off some of our power to bias the A amplifiers. Make sense? So I'm not going to go through the details right now. We'll see points a little bit. But if you look at the GB power efficiency of this structure, what are we going to conclude then?
It's worse.
It's a little bit worse. For a given power, we're going to have a little bit less GB for this structure than we do for the reference op-amp and than we do for the telescopic Cascode op-amp, because we need to siphon off a little bit of power to bias those A amplifiers. Is that good or bad?
Just depends. It depends.
Yeah, it just depends. If gain is really important, then maybe you're willing to sacrifice for a given power. Maybe you're willing to sacrifice some GB. So this does not help GB, and it slightly hurts it. Well, here's our telescopic gain boosted telescopic Cascode op-amp. Create our quarter circuit. Here's the quarter circuit. Replace it with N with P's, P's with N's. Put them together, form a half circuit, fold it over, get the full circuit, and bias in the tail with your choice, a current source or voltage source. Right now we need a common feedback circuit to bias either M11 or M5 and M6. And biasing is going to be a real challenge here, because this DC gain has maybe gone up another factor of 40 dBs. Anytime you have a really high gain circuit, I mean, now we're starting to look at a circuit that's talking about maybe 120 dBs type of gain. This is a really high gain amplifier. If you have even a slight DC offset at the input, and you multiply it by 1,000,000, it'll saturate the output. Make sense? So biasing is non-trivial here, or is important, because we've got such a high gain on this structure. But we can connect the counterpart circuit as a current mirror if we want to eliminate the combo feedback circuit, and use the differential op-amp to facilitate biasing of the Cascode device. This reference op-amp is oftentimes used for these right here. Somebody want to write down the gain expression for the circuit? So what do we need? GM of the quarter circuit, G out of the quarter circuit, and G out of the counterpart circuit, right? If we get these three things, we can write down the overall gain and gain bandwidth product by inspection. Volunteers. G out of the quarter circuit. George, I'm going to volunteer you. G out of the quarter circuit.
With the G out 1 over G out 3 Or,
So we start out with G out 1, and we improve on that. So it's G out 1 times
G out 3 over GM 3.
G out 3 over GM 3 times
1 over A.
times 1 over A. Okay? And G out of the counterpart circuit will be G out 5 times,
Yes.
you guys are good, over GM 7 times 1 over, I call that A3. The A's are probably the same. And GM of the quarter circuit is equal to GM1. Fantastic! You've analyzed the circuit. If I did this in MATLAB, I'd have pages and pages and pages and pages of output. But only about 3 terms in 20,000 expressions would probably be, or whatever, would be relevant, excuse me. So here's the gain. Here's the gain bandwidth product. And as I pointed out, this is modestly less power efficient at generating GD. Because now the total power is not going to determine GM1. Part of the power is going to get funneled off onto the A amplifiers. Yes?
Now, when we use the BSIM model in the lab or in Cadence, can we count on it doing something closer to what we see in MATLAB than what we do on paper?
Absolutely.
And that
Absolutely.
can kind of be our balance, right? Of
That's right.
accuracy and insight.
That's right. Exactly. Yes?
So I don't know if you said it before, but did we decide what kind of amplifier A is? Because won't the equation get more complicated once we figure out A for those amplifiers?
Yeah. Yeah. So the A is usually a 5 transistor amplifier.
Okay.
And we usually singulated output on A.
Yeah.
From the,
Yeah.
So this is the output, and you'll put one of the terminals to, we call the voltage Vx, I think that terminal. And the other one will connect to Vx desired, the requested value that we want for that. That means these two voltages force the same, the input is on here, the output's here. So this is typically what we use for that A amplifier. But it's a good question. Why don't you think we use more complicated structures for the A amplifier?
It's very complicated in our stuff.
Yeah, it's probably a good point. We don't want to burn any more power than we have to in that A amplifier. We want a reasonably good frequency response. You're going to find that this A amplifier here is really, we're going to have a hard time beating that very much. The first one we started with, the simple one we started with, we're going to have a hard time beating that very much from a power efficiency viewpoint. And most of the other amplifiers we're going to look at are going to have more gain or more signal swing. We know what the signal swing here is. We don't need much signal swing on this node. And I don't know that we need more gain. I mean, we're already up. When we go to the regulated cascode structure, we're already up in the 100 to 120 dB gain range on our op amp. There aren't many applications in the world that require op amps that have a gain bigger than this. So what advantage would we have of putting a bigger A amplifier? Well, if the gain of the amplifier was bigger, we get more gain of our overall amplifier we're building right now. But at some point you say that's good enough. Does that make sense? We're getting really high gain. Here we've eliminated the common mode feedback circuit by connecting the counterpart circuit as a current mirror. And as before, modestly less efficient. If you look at the structure, it has a similar limitation to signal swing. As with the telescopic Cascode, we've got 5 VD-SAT drops between VDD and VSS. So that's a disadvantage. Now, if you look at this structure here, the signal swing is even a little bit worse because this voltage here is VD-SAT plus the threshold voltage. And that voltage and this voltage will be the same, and consequently this is VD-SAT plus a threshold voltage plus a VD-SAT plus a VD-SAT plus a VD-SAT plus a VD-SAT. So our signal swing is limited to VDD minus VSS minus 5 VD-SATs minus VTH. So this improvement in gain is at the expense of a modest loss in signal swing. There's a pole in the A amplifier, or each of the A amplifiers, and so we really have to contend with a second pole here, which may introduce some issues in regard to phase margin that we might have to address. However, the A amplifier is usually designed to have a really wide bandwidth, so hopefully that amplifier doesn't hurt you too much. But if you make the A amplifier have too wide of a bandwidth, it eats up power. So you have a limit on how much power you can push into the A amplifier because that degrades the GB of the op amp you're trying to build. The area overhead for this is 4 amplifiers. The area overhead is usually not of concern here. If the performance is needed, then we can usually justify the area overhead. But the power overhead is more of a concern. Well, we had pretty good luck here working with simple circuits and coming up with operational amplifiers. By the way, if you go in your textbook, these amplifiers we talked about, they're all part of what they call their high-performance op amps that are discussed in your textbook. Are there other useful high-output impedance circuits that can be used for the quarter circuit? Let's keep playing this game as long as we can. Oh, by the way, most people don't look at it this way. Most people don't look at it this way. I made a statement earlier. I think anybody in the class, if they wanted to, could come up with a current mirror that's new. I suspect that if people looked at quarter circuits, different quarter circuits, simple structures create quarter circuits, you create some op amps nobody's ever envisioned that might have properties that are pretty attractive. Does that make sense? What's this circuit? No mistake there. There's not a mistake in the drawing.
It's just a half circuit from our reference. A little more.
So if we're going to try to pull the quarter circuit out, this would be the quarter circuit, right?
Yes. Right.
From a small signal viewpoint, what does this circuit look like? No. Well, it is technically a cascade. How does that differ from a small signal viewpoint? How does that differ from this circuit?
It's just a common base.
How does this one differ from this one from a small signal viewpoint? What?
Yeah, it should flip that.
We have the M3 will also behave as an amplifier versus just a
So the drain of M3 goes into the drain of M1 goes into the source of M3 here, right?
Yes. But, and since we have a current source biasing, we don't have M3 stays a 2-port in the small signal. It won't become a 1-port model.
So when you look at this one here, we had a current source here too, right? I bias. What did we call this one previously? The circuit here.
We call that a cascode.
We call it what?
A cascode,
This is the cascode starter, right?
yeah.
How does this small signal, so here was the quarter circuit, we pulled out of that cascode. How does that quarter circuit compare to the small signal circuit, compared to that we pull out of here?
It's the same, isn't it?
The same, identical. Oh shucks, nothing new.
Because your VDB will go to ground. That's everything else the same. Source is coming through the drain.
Okay, architecturally it's the same. We stuck a P channel instead of one of the N channels in there. Does everybody see that?
Yeah.
So this is still the cascode configuration. That's the good news. They're both a cascode amplifier. So we would expect the characteristics to, from a small signal viewpoint, we'd expect what? The same.
Except we know intuitively the P channel has less mobility. So gains
Okay, so numerically there may be some differences between the two, but keep in mind, we still are stuck with that P-channel device in the counterpart circuit. So here we get that nasty P-channel device in the quarter circuit, but it puts an N-channel device back in the counterpart circuit. Maybe that's not so bad.
Yes.
Okay? Our gain expression should be about the same too, because they're based on small signal analysis. And small signal models are same, identical. We have a special name for this circuit. It's called the folded cascode amplifier. But there's a problem with this circuit. If you look at the current that flows through an N-channel transistor, to keep it in the saturation region, has to flow from drain to source. To keep a P-channel transistor operating in the saturation region, has to flow from source to drain. So we got a problem here. It doesn't work. That's a big problem. We can't bias it. It looked great from a small signal viewpoint, but this current has to go in this direction, and this current has to go in this direction. Is that a major problem?
Yeah.
Anytime it doesn't work, it's a major problem. How about this one, though? There you go. How does small signal equivalent of this one compare to the one on the left? They're the same. But now, it could be the case, we have a current flowing here. If this was, let me say this, assume this is 1 milliamp. And if this was 1 milliamp, and this was 0.5 milliamps, then we'll have a net current flowing in this direction here. So we have now the ability to bias both M1 and M3 so that they're in the saturation region. So eureka, we're back in a situation now where it'll work. And the small signal analysis is the same. Now, we had a lot of effort, though, to salvage the circuit. We come up with this folded cascode circuit, and it doesn't appear to offer any better, and a lot more effort to bias it. So here's an implementation of that current source in that folded cascode structure. We could put a better current source. Whoops, I'm out of time. Okay, so let me leave it here. Give some thought to whether there might be some use for this structure. I'm not trying to waste your time. There's some limitations we see, more complex biasing. Wonder if there might be any benefits. Any questions? That's all for today, thanks.